The t-test is really great, it's really commonly used, but it is fundamentally limited to testing for differences between two groups, exactly two groups. If you have more groups or if you have a more complicated design, you need to supercharge your t-test, and that is where we get to Anova. Anova stands for analysis of variance, and the goal of an Anova is to determine the effects of multiple categorical independent variables on a numerical dependent variable. So notice we're mixing different types of variables here. We have numerical variable for the dependent variable and categorical for independent variables. I'll give some examples in a moment so you can get an idea of what this means. Oftentimes when people talk about ANOVAs, they precede the word ANOVA by talking about something about the design of the ANOVA. So one thing that they say is a n-way ANOVA, where n would be the number of factors. So for example, we have a one-way ANOVA. That means we are looking at one factor, and we might be determining the influence of the day of the week on iPhone purchases. So we want to know, are people more likely to buy iPhones on, Thursdays and Fridays and Sundays, and less likely to buy iPhones on Wednesdays and Tuesdays and Saturdays, and least likely to buy iPhones on Mondays. So there we have the independent variable is categorical and the dependent variable is numeric. And here we have one factor. We're just looking at day of the week. So that's a one-way ANOVA. Here would be a way to change this into a two-way ANOVA or a two-factor ANOVA. Let's say we're determining the influence of day of the week and gender on iPhone purchases. Maybe men buy iPhones more during the week and women buy iPhones more on the weekends. I don't know. That would be an example of a two-factor ANOVA because we have one factor for day of the week and one factor for gender. And still the dependent variable is numerical. Another type of ANOVA is called a repeated measures ANOVA. And a repeated measures ANOVA means that at least one factor involves multiple measurements from the same individual. So let me give you an example so you get to see what this is like. So let's say we are determining the effects of snack type on mood. This would be an interesting experiment. So we have our research participants, and they come in, they eat chocolate for 2 days and potato chips for 2 days and ice cream for 2 days. And then we ask them about their mood on each of these days. Now I know what you're thinking. Where can I sign up to be part of this experiment? Well, this is just my thought experiment. Anyway, so here we have, in this case, one factor. So this will be a one-way repeated measures ANOVA. The factor is snack type, and it's repeated measures because we have the same individuals on multiple days going through each of the different levels of this factor. Of course, we could also extend this to be a two-factor repeated measures ANOVA. Let's say if we were also looking at gender in this case. So maybe men are in a better mood when they eat potato chips and women are in a better mood when they eat chocolate. I don't know, just making this stuff up, but this gives you a sense of how a two-way repeated measures ANOVA would work. Now remember I showed you the formula for a t-test where we were looking for the difference of means divided by something about the dispersion or the standard deviation in the data. So with an ANOVA, we get f-tests, and the f-test is a little bit similar to the t-test. It's analogous to the t-test, where we're looking at a ratio of variances. So we want the explained variance divided by the unexplained variance. And another way to explain this is the variability in our data that we can definitively attribute to the different factors that we are looking at, for example, the day of the week, or the gender, or the snack type. Those are the factors in the experiment that we have control over. So we can call that explained variance. And then there's just the natural individual variability. Different people behave differently. They have different preferences. So that is the natural variation. So when we have more variance in the data that we can explain from our factors, from our experiment design, compared to how much variation there just is naturally in the data, then the F ratio is going to be large, and then we're more likely to get a statistically significant effect. Now, when you run an Anova, you are going to see a really big, messy table. Looks like this. There's a lot going on in this table, and explaining all of these things takes a little bit longer than the amount of time that I have here. But sometimes these Anova tables are just there to confuse you. There's a lot of stuff in here. You don't have to pay attention to everything. The most important information in this table is the factors here, the names of the factors, and the p-values all the way here. In fact, all of this stuff in the middle is just showing you step by step how the p-values are computed. So when you see an Anova table like this, just don't worry about all this stuff in the middle. You want to look for the p-value. It's usually the column all the way to the right, although not necessarily. Sometimes there's even more information to the right. But you want to look for the p-value column and the names of the factors. So going back to one of the examples I mentioned earlier, let's say we have the factor day of the week and the factor gender and the interaction. So the factor day of the week means that people are in general more likely to buy iPhones on the weekends compared to during the week. And gender is, I don't know which gender is more likely to buy iPhones. Maybe there's not going to be a significant effect of gender. So this p-value would be close to 1. And an interaction would mean that, men buy iPhones more on the weekends and women buy iPhones more on the weekdays. So that would be a significant interaction between these two factors. Now, one thing to keep in mind about the p-values here is that the p-value just tells you that the factor itself is significant. It doesn't tell you which group or which level is different from which other group or which other level. That requires further data visualization and follow-up t-tests. So for example, if we find a significant effect of day of week for the iPhone purchases, the p-value just tells us that some days are people buy more iPhones and some days people buy less iPhones. We're going to have to do subsequent data inspection in order to figure out which days are more likely to have iPhone purchases.